So, I recently realized that there's nobody doing jokes about LLMs. So, before I invite our speakers, I wanted to try a couple of things with you guys. All right. So, who knows why did Yoda get frustrated with the LLM? Understand my syntax? It does not. All right, that was good enough. All right. I'll give you the second one, which is why did the transformer model go to therapy? It needed more attention. That got better laughs. Thank you. I appreciate that. All right. So, we'll start with our agenda. We have a pretty full agenda today. We have 3 talks. Feedback. Suleman will talk and walk us through a lot of details about structured outputs and function calling. Then we'll go and Nikhil will talk about the enterprise data architecture and how to build actual, systems for RAG. And then Rogger will talk about strategies for mitigating hallucinations. So we have, a different Rogger with 2 Gs. Yeah. But if you want to join and help out, we might have something at the end. Anyway, so that's the agenda. I just wanted to highlight we have an event survey. This is the QR code for it. So at the end, if you are so willing, we would love to get some of your feedback. And we also have a Slido for Q&A. So if you have questions that you don't get to ask live and you want to ask them in that Q&A form, they'll be great too. I'll post those also at the end of the event, but just if you want to take a minute and take those QR codes, this is also for people who are on the live stream. And without further ado, I'd like to invite Suleman to give us the first talk. Thank you.
Thanks, Ofer. Just start. Okay, so hi everyone. Thank you for coming. My name is Suleman Kazi. I'm a machine learning engineer at Vectara, and I'll be talking to you about structured output, function calling, also known nowadays as tool use, and how do you use it with large language models. We'll be covering what these 2 things are, differences between them, how do you fine-tune an LLM for this purpose, how do you guarantee structured output, and then we'll have some hands-on collabs and a nice demo tying it all together, showing you how to do agentic RAG, which is essentially combining tool use with RAG as a demo. So let's get started. So what's structured output? Structured output's kind of obvious from the name, is where your LLM is producing output that adheres to a certain syntax. So for example, whether that's JSON, whether it's outputting a CSV, XML, whatever. So that's structured output. To give you an example, let's say we ask an LLM, in this case, the output that you see here is generated by GPT 3.5, what the 3 tallest mountains in the world are. The LLM, I don't know if that height information or location information is correct, but it does give you some output about the 3 mountains, notable facts, location, and whatnot. But let's say we don't want it this way. Like, for example, if you want to put it into a database downstream, or if you want to pass this information into a function downstream, like parsing raw human readable text isn't exactly ideal. So let's say we want it in JSON format. So the easiest thing to do there, just ask the LLM, give me the answer as a JSON structure. And, again, this is GPT 3.5. It does a pretty good job at giving you a JSON output for the largest, tallest mountains, height in meters, height in feet, location, notable facts. But, it's kind of deciding what fields need to be in the JSON on its own. And for example, if you're calling a function downstream, or your data set might not even have these columns in it. So what do you do then? Well, you can give it your prompt, which is tell me the 3 tallest mountains. And then I've put it here as a plus. It depends on what LLM you're using, but essentially you give it a JSON schema in some way. So for example, in this case, you're going to say the JSON output should only contain the mountain name, the height in meters, and the country where it's located. And if you do this with GPT 3.5, it does a pretty good job. It gives you the mountain name, the height in meters, which now is an integer rather than a string or a floating point number if that's what you want, and also the country which is in. There's still one thing wrong here. Can anyone tell what that is? So see, we wanted the country as a string, but it's giving me two countries separated by a slash. Now that with GPT 3.5 is something you might not be able to fix, but we'll talk about using LLMs off of Hugging Face, and that's something you can definitely fix there with some structured output libraries. And we'll talk about that in the hands-on section. Okay, so that's it for structured output. What's function calling, aka tool use? So function calling essentially allows LLMs to produce output that can be interfaced with external systems, other APIs, other tools, and so on. And think about this. So let's say you're building a home assistant, right? And you want the assistant to book a meeting on your calendar for tomorrow or whatever. Now, with a standard LLM, if you ask it to do that, it's just going to produce text output. It's not really going to take any actions for you, right? So this is an example. So let's say we have an LLM or an assistant, and we're asking it what the weather is like in Palo Alto tomorrow. If it's not raining, can you reserve a table for me at a restaurant? If you ask any standard LLM, like GPT 3.5 or whatever you get from Hugging Face to do it, you're probably going to get something like this, where it says, I'm unable to provide real-time weather updates or reserve tables. I don't have access to real-time data. And in some cases, I mean, this is a good response. Like it's telling you it can't do it. In some cases, it might pretend to make a reservation for you and say, okay, your table is confirmed. And you show up the next day and you're kicked out. So, and function calling or tool use essentially solves this problem, where if you tell an LLM to do it, it's gonna, well, let me be clear. The LLM isn't gonna take the actions for you. The LLM is gonna tell your orchestration framework, which is just a fancy way of saying the bits and pieces of Python you have around your LLM. Hey, can you take this action? Can you call this API or tool and make a reservation for you? And what that looks like is similar to what we had with the JSON example, where you give it a JSON schema. In this case, you give it a list of functions or APIs that you have access to, which I'll show you on the next slide. So for example, for a request like this, it might need access to some functions. So for example, a function which gets the forecast, a function which gets the current date, a function which makes a reservation, and so on. And you also have to tell it the description of the function. We'll get into the syntax on the hands-on section of this, but essentially you describe the function and tell it what it has access to, and then it can take action on it. So what would that look like? So for example, for an LLM which supports tool use, the user would say, what's the weather like in Palo Alto tomorrow? If it's not raining, could you make a reservation? And the assistant would then say, an assistant which has access to these functions would say, can you please, would ask the user essentially, can you please call this function called get current date? Because it doesn't know what tomorrow is, right? Like it doesn't know what tomorrow is until it knows what date it is today. So the user would then call the function. The user would say, okay, LLM, I've called the function. The function told me today is 19th of June. And then the LLM would say, get forecast. Can you call the get forecast function for Palo Alto for 20th June? Because now it knows today is 19th. The user would say, okay, here's what the forecast function returned. LLM would look at it and it's like to rain in Palo Alto tomorrow. I'm not making a reservation for you. So, and this isn't, we'll get to the hands-on section, so we'll do a demo for this. So what's the difference, or like what are the similarities between structured output and function calling? As you can see here, the function calling LLM also has to produce structured output, right? So it has to produce a valid function call, which in this case, the syntax is again a JSON object. It can be different for different LLMs, but the most commonly used one is a function call as a JSON object. And so function calling is almost kind of a superset of structured output, where the LLM not only has to produce structured output, but basically has to determine when to produce that structured output. So for example, in this case, for the last turn, it didn't call a function because it knew it was raining, and the user only asked me to make a reservation if it was not raining. So for function calling, the LLM has to be somewhat smarter than just producing structured output. So moving on. So let's say, and this is kind of an aside, like if you don't want to use an out-of-the-box LLM that supports structured output, like if you want to train your own LLM for structured output, how would you do that? How you train LLMs for any other task, essentially, which is fine-tuning. And what would the data set look like? So this is an example from a data set that's on Hugging Face. It's called the glaive function calling data set. And this is what an example data example looks like for an LLM that you would train for function calling. So essentially the data is like you're a helpful assistant, you have access to the following functions called create calendar event, and then you give it the description of the function and the arguments. And then you kind of give it a mock conversation. So the user's like, can you help me create a calendar event for my meeting tomorrow? The assistant's like, yes, I can help with that. But then if you look at the function description, it actually needs some parameters which the not specifying. So it needs the start date of the event, the start time of the event, and then the LLM has to be smart enough to kind of get that information for the user. So it says, I can help with that, but could you please provide me with the title of the event, the start date and the end date and so on. And the user provides that information, and then the LLM says, function call, make this function call, and so on. So that's what the training data looks like. Now, you don't need to train your own. It's expensive. You need GPUs. So you can use an out-of-the-box model for that as well. There are a lot of models on Hugging Face which are focused on tool use. These are some of the names. I think Gorilla LLM, that's from Berkeley. Gorilla Open Functions, this one's from Nous, I don't know how you say it, research called Hermes 2 Pro. There's Natural Function, and then the latest version of Mistral 7b v0.3 actually also includes function calling. And one good way of finding models is like you basically go to Hugging Face, look at the data set. So this is the data set I was talking to you about. And there's models trained on this data set, and you click on here, and you can see all the models which use this data set. So they do have some element of function calling in them. And you can sort by trending or most downloads or most likes or whatever you like. So that's that. So one thing, like fine tuning gets you 90 to 95% of the way there. So for example, if you fine tune an LLM on a structured output or function calling data set, sure, 90% of the time it's gonna produce structured output. What about the rest of the 5%? There is a way to guarantee structured output. It's called constrained decoding. And what that essentially means is when the LLM is producing output, you manipulate the output so that it's impossible for the LLM to produce an invalid next token. So for example, if you're producing JSON, JSON has a particular syntax, right? There has to be a closing bracket at a certain place. There has to be a comma at a certain place. So when your kind of constrained decoding tool or framework realizes that the next thing can only be a comma or a closing bracket, it sets the probabilities for the next token to be anything else than those to be 0. So the LLM is kind of forced to produce output that way. And it's not something you have to set up on your own. There are frameworks and libraries which help you do that. My favorite one is called Outlines, which lets you do JSON. You can specify a regex. So essentially, the LLM output is going to match that regex. You can do your own grammars and so much more. And if you're serving your LLM, VLLM, which is like a very popular serving tool for LLMs, already has outlines integrated. So you can just specify the schema in the request, and it will do that for you. Okay, so I think that's enough talking about the theory of how to do things. We're going to move on to an actual code example of how you do it. And I have 2 examples. One's for if you want to use OpenAI to do it, and the other one's for if you want to do a self-hosted LLM in Hugging Face and do it that way. So let's start with the OpenAI example. So is the size fine? Can you guys see the size at the back? Or do you want me to zoom in?
That's good.
Okay. So this is just some standard boilerplate for calling the OpenAI API. We're gonna install it first. I should have done that before. We're gonna use GPT 3.5. You don't really need a model that's too fancy for this. Like GPT 3.5 does a decent job at it. What I want to show is like in order to do function calling or structured output, there are some additional parameters you need to send to the chat completions API if you use that before. So essentially the model is the model you're using, which is GPT 3.5 Turbo. Messages are like the conversation that's happening. Response format, we'll see that in the structured output, and then you give it a list of tools and tools choice. So essentially tools are the functions you provide to it that it can call. It can choose to call. And then tool choice is an interesting one. So basically tool choice, which if we use auto, that means you decide which functions you want to call and when you want to call them. If by tool choice, I give it one of the tools here, that means it has to call that tool in that turn. So that's up to you if you want to leave that to the LLM or if you want to enforce usage of a particular tool. Again, some boilerplate about printing the conversation. So let's start here from unstructured output. So the example I showed you about the 3 tallest mountains, we're just going to prompt it with what are the 3 tallest mountains in the world, what are their heights. And the system message here is just your helpful assistant, answer user queries. And we're gonna print what it says. Oops, I didn't run this. Yeah, so basically, similar to what I showed in the slide, it tells you about the 3 tallest mountains in human readable text. Let's see if we can structure that with a prompt. So now the prompt changes to what are the 3 tallest mountains? Give me the answer as a JSON object. And let's see what it does. Okay, so it gave you a valid JSON object, mountains, the name of the mountain, the height of the mountain. But as you can tell here, maybe this isn't something we want. Like, what if we want height to be an integer? It's giving you the height in feet and also in meters. What if we only want it in meters? What if we also want the location of the country or place where the mountain is located? So that's what we'll do next. So OpenAI has this mode called JSON mode, which essentially constrains the LLM to output stuff that is valid JSON. Now, one important thing to note here is that JSON mode guarantees that the output will parse into a valid JSON object. It does not guarantee that it will match the schema that you give it. It's pretty good at matching the schema, but it's not guaranteed. And we'll see in the next collab where you run a local model that you can actually do that with the outlines library. So let's do that with OpenAI here. So the prompt here is format your response to the JSON object, and then we give it the schema. So for example, we say the name has to be a string, height has to be an integer, and in the description we say, okay, we want it in meters, not in feet or some other unit. And then the location is the country the mountain is located in. And then we ask it, what are the 3 tallest mountains in the world? So let's see what it does here. Okay, so in this case, the output is a valid JSON object. You have the name of the mountain, the height. Notice it's not a string. It doesn't have the quotes around it. It's in meters. And then the location, as we discussed, it's still wrong. It's not one country. But I mean, mountain can be in 2 countries, right? So I don't know. But anyways, that's what it makes. So that's kind of the structured output you can get with the OpenAI API without using any external libraries. That's kind of baked into the OpenAI chat API. But what about function calling? So let's move on to the second part called function calling. And in function calling, as I mentioned, you need to give it a list of tools that it needs to use. And this is how you do it. So you give it the functions, the name of the function, the description, the arguments, or the parameters. So for example, the function is called make reservation. It makes a reservation at a restaurant. It needs the name of the restaurant. It needs the date. It needs the time, and so on. And I've kind of manually written this out, but you don't need to manually write it out. Like you can write this function as a Python function, and there are tools. For example, there's one from LangChain called convert to OpenAI function, which will look at that Python function and its docstring and convert that to kind of this description that you can then pass on to the OpenAI API. So we give it the make reservation function, we give it the get current date function, get forecast, and so on. And then we ask it, what's the weather like in Palo Alto tomorrow? If it's not raining, can you make a reservation for us at Zareen's restaurant at noon? And so one more thing I should explain is, so actually let me explain that in a bit. So we're gonna give it the messages, which again, the system prompt here is just your helpful assistant, answer queries informatively. And we're telling it, don't make assumptions about what values to plug into functions. Ask for clarification if a user request is ambiguous. And that's because if I make a request about, for example, that doesn't include the number of people or the date or the time, it should ask me about what date I want the reservation at or what time I want it at. And in this case, these functions are just defined here in Python as dummy functions, and they just return, reservation is made, or the current date is this, or the weather is this, location will be rainy. In reality, if you're making like a function calling tool use system, these will probably be external APIs that you call. So like something from weather.com that gives you the forecast for a particular date. And then this is just some boilerplate code, which takes the message from the assistant, like the thing that ChatGPT returns, and tries to figure out whether it's telling you to call a function or not, and then actually calls the function and gets the value back to your LLM. So let's start. And one important thing to note is that LLMs really don't have a concept of state. So every call you make to an LLM, it won't know about the previous state until you append that previous state into the entire conversation. So that's what we're going to do. So we're going to call the LLM. It's going to give us an output. we're going to append to that output and send the whole thing from the beginning of the conversation to the end back to the LLM. So there's no concept of state there. Okay, so let's start. So what we're going to do here in the first iteration is we're going to send just the prompt, what's the weather like in Palo Alto tomorrow? And we're going to pass in the tools. So basically, in the function, like in this call, sorry, I should scroll. Yeah. So basically, in this function for chat completions, the tools are going to be the functions I just showed you. The tool choice, if you don't specify it, it's auto. And then the model we're going to be using is ChatGPT or GPT 3.5. So let's get to here and let's call it the first time. Oops, I haven't run the previous cells. Okay, so we define the tools, we define the functions, and we send the first message. So let's see what the conversation looks like. Okay, so the user said, what's the weather like in Palo Alto tomorrow? If it's not raining, can you make a reservation for us? This debug string, essentially, it's not a part of the conversation itself. I've just put it there so you can see what's happening. So what was returned from the LLM was like the LLM requested a function call, and the function call was get current date with no arguments. The Python code surrounding the LLM, this part, went and executed the functions based on the message. The function it executed was get current date function returned the current date is this. And this is then appended to the conversation that gets sent to the LLM. Now we're going to run it again, and this time we're going to send this whole text to the LLM. So the LLM, as the next step, now that it knows the date, requested the function call get forecast. The location it knows from the user message is Palo Alto, and the date it now knows is 20th of June because it knows the current date is 19th, and we requested for tomorrow. And the function said the weather in Palo Alto will be rainy with a high of this and a low of this. We send this to the LLM again, and the LLM says, I'm sorry, but the weather forecast predicts rain. Would you like to make a reservation for another date? So it's smart enough to know I shouldn't be calling the restaurant API to make a reservation. So let's actually change this. So let's see what happens if we say the weather will be sunny. Does it actually make the reservation or not? So we update the get forecast function. So tomorrow is going to be sunny. And we will have to reset the messages. So we start from there. And we send a request again. So again, like the first time, it gets the current date. We run it again. It gets the current weather, will be sunny. We run it again. And now you see the LLM is actually calling or requesting a call to the API for making a reservation with the date, the time, and the restaurant. And then the function that actually makes the reservation says the reservation has been made. And if we run it again, it's like the weather in Palo Alto tomorrow will be sunny and the reservation has been made for you. And in this case, the reservation is actually made. It's not just making stuff up because it has called the function internally. Yeah, so that's basically how function calling works with LLM. So one more thing is like, you see me running this loop again. So I've essentially manually unrolled the loop here. When you actually run it, and we'll see it in the next Colab, is you'll have some form of recursive for loop or something, which kind of looks at the LLM output, sees whether a function call is needed, makes the function call, sends it to the LLM, makes the function call, sends it to them. But just for demonstration purposes, so you can see how the conversation unfolds, I'm kind of manually unrolling the loop and running it one at a time. So that's it for the OpenAI function calling. How about we want to do the same thing with a Hugging Face model or your own model? So for that, I'm going to switch to Visual Studio because the GPUs provided by Colab aren't good enough to run bigger models. I'm going to run this on a GPU machine. So again, starting from there, the model we're going to be using. Do you guys need me to zoom in, or can you see at the back?
Zoom in.
Okay. Yeah, let me close this. So let me close this. Okay. So basically, we're going to be running on CUDA. The model we're using is Mistral Instruct 0.2. We load the model. And in this case, this is just boilerplate for running the model, getting the output, and printing the conversations. We're going to do that. So let's start with the same thing we started with OpenAI. just an unstructured prompt. What are the 3 tallest mountains in the world? What are their heights? And we send it to the model. And this is going to take longer because it's running on a local GPU and it's not fast. And I believe I have forgotten to quantize the model. But anyways, here's the output. The assistant says 3 tallest mountains in the world are these. Human readable text as you would expect. So let's ask it nicely to give you the output as a JSON structured object. So in this case, the prompt is the same, but you just append, give me the answer as a JSON structured object. And the assistant says the mountains are these, the name is Mount Everest, height in meters. So this time it was smart enough to actually make this an integer, unlike GPT 3.5. But let's say we just want height and not height in feet. That's where the outlines library comes in. And before I show you the mountains example, I'm going to restart because outlines loads its own model and I don't want 2 models in the GPU. RAM is probably going to run out. So outlines is the library I was talking about, and it's pretty easy to use. What you do is instead of instantiating a model with the Hugging Face API, you load it with the outlines.models.transformers. And I believe it can take pretty much any model that conforms to like a generative Hugging Face model. So let's start that. So it loads the model. And before I get to the restaurant example, this is another interesting example I want to show you. So let's say you want to use an LLM as a classifier. I'm not saying that's a good idea, but let's say if you want to do that. And you wanted to review restaurant reviews. So we say you're a sentiment labeling assistant. Is the following review positive or negative? And the review is this restaurant is just awesome. Now, if you were to do it on its own, LLM would say the review is positive, or the review says the restaurant is good, or something along those lines. But if you want to use this to, for example, generate synthetic training data for training an actual classifier model that's smaller than an LLM, you want your training data to be deterministic, like have a label of 1 or 0, or in this case, positive or negatives. So with outlines, you can just say outlines.generate.choice, and you give it the choices. So the model is constrained now, and it can't output anything except the string positive or the string negative. So let's see what it does. So in this case, it says the review is positive, which is fine. The review is positive. Another example of this is, for example, if you want to make an LLM do math, which is an even worse idea. So let's say you want to give it what's the result of 9 plus 9 is 18, result of 1 plus 2 is this. It might say 3 as a string 3, but with outlines, you can kind of constrain it and say your output should be an integer and nothing except an integer. And similarly here, if you want to find the square root of 2, you can say your output should be a float and nothing but a float. So let's see what it does in these 2 cases. Okay, so it says 2 plus 1 is 3, which surprisingly it got right. And then square root of 2, it says 1, which as expected, it got wrong. But it still got the syntax right, like 1.0 is a float. So I think that kind of reinforces the point. Like outlines will enforce correct syntax. It will not enforce correct semantics, or it will not guarantee correctness of the output, just the correctness of the format of the output. So going back to our mountains example, again, we're going to give it the JSON schema. And with outlines, what we can do is we can say outlines or generate.json. And now the model output will correspond to that JSON schema. So we say, what are the 3 tallest mountains in the world? What are their heights? I'm not a fan of mountains. Like if you're considering that, I don't know why I chose that example. But anyways, let's see. Oh, I didn't import JSON, but. Okay, let's run this again. Okay, so it's outputting something, but it's not outputting the right thing. It's saying Kunlun Mountains in Asia, whose height is 5128. We asked for the 3 tallest mountains. We didn't ask for 1 mountain. And this is not the tallest mountain. Like Mount Everest is the tallest mountain. So what's happening here? Anyone have any ideas? Anyone? Okay, so what's happening here is essentially with outlines, we constrain the output to be correspond to that JSON schema. But in the prompt, the model has no idea that it's going to output something that when it's generating, someone is going to force it to output JSON. So let's do it this way. Let's do the same thing, but in the prompt, we're going to say give the answer as a JSON structured output. And let's see what the LLM does in that case. And it's going to take a while. It's generating the output on some GPUs. Okay, so now it looks much better. It's giving you the 3 right mountains with the right height and the right locations, the same as what ChatGPT was doing. So that's much better. I am slightly running out of time, so I'm going to skip so I was going to show you 2 LLMs with function calling, so I'm just going to show you one. But we're going to release these collabs so you can play with it on your own. The one I'm going to show you is called the Open Hermes function calling model. And what that model does, so remember, like I said, the Python thing I was running manually every time with the loop, it kind of gives you a nice scaffolding for doing that on its own. They have a repository which I've put here, which you can download. And in that repository, you can provide your functions like I've done here. So in this case, you don't need to specify them as a JSON schema like I was doing. You can just write them as a normal Python function. You put this decorator on top of it, and then you call convert to OpenAI tool, like I'm doing here, and it will automatically convert the doc string for your function and also the function arguments to exactly the type of JSON that I was showing you earlier. So, and the scaffolding kind of looks like this, where they have a model inference thing, which loads the model, runs inference, looks at the model output, extracts the function calls, goes and runs the model. So it's a more sophisticated way of doing what I was doing in that collab. So let's see how an open model does. I'm trying to find the command that I was running, which kind of looks like this. So let's see. We're going to ask it to do the same thing we asked GPT-3 to do. What is the weather like in Palo Alto? Can you make a reservation if it's not raining? And in this case, what I've observed is that with open models, again, it's the 7B model. GPT 3.5 is a much larger, much higher quality. It can sometimes get the stuff right, but sometimes it gets the stuff wrong. So let's look at what it output once it finishes. Okay, so let's look at the output, which should be somewhere here. So these are the logs. Okay, so let's see what it did and if it did the right thing. So the assistant said to find out the weather forecast and make a reservation. And I'll start by getting the weather forecast for Palo Alto on June 21st. So yeah, in the function call, I asked it for June 21st, not for tomorrow. So it's calling. So this is essentially what it looks like. It says tool call, and you have to parse that out of the return string and call the function with these values like location Palo Alto, date 2024, get forecast, and then the scaffolding around it invokes the function call, sends the response back to the model, the weather in Palo Alto will be sunny. Assistant gets it, says, okay, it's sunny, I'm gonna make a reservation, calls the make reservation function, and then says I successfully made a reservation for 2. So in this case, it works. Let me try again to see if it works again, but yes, 1 in 4 times it'll fail. But that's LLMs for you. Unless you use them with Vectara. So. Okay, so it actually passed again. Well, that's surprising. But anyways, sometimes it'll fail. Sometimes it'll say, I should call the function and won't necessarily tell you to call the function and just tell you I've made a reservation, it's confirmed. But this is generally how you would use it. So basically, that's what I had for this presentation. I'll hand it back to Ofer, who's going to show us how to kind of do all of this in a much more production-oriented way to make an app that you can actually show to customers rather than collabs that I'm showing you. Thank you.
Thank you, Suleman. Thank you. This was awesome. And wow, what a good level of details. I'm a little disappointed that tomorrow I can't go eat lunch at Zareen's because I love that place. So I just want to show one more thing, which is something that's coming soon from Vectara. We call it Vectara Agent. So as you know, this whole stuff about function calling and tool use there's a lot of work on it and a lot of different things. And so we're creating this library that you can just pip install Vectara Agent, and you'll be able to create tools. You'll have the whole sort of agent framework that does all this function calling and tool use in a very easy way, using Vectara as one of the main areas you can use tools for. So please stay tuned for that. That'll come pretty soon. It just makes everything really easy. You can create agents of different kinds. And I'll show you one of them. This is an example agent I created with the kind of the private beta and the private beta of Vectara agents not yet available for financial chat, and I want to show you why it's good to use that way. So crawled a bunch of 10Ks and analyst transcripts for a bunch of companies and public companies from the years 2020 and to 2024. And then I gave this agent essentially two tools. One is this tool called Vectara Ask Analyst, which essentially does a RAG query on top of all this text. And then another one that actually calls an API that's paywalled, something that we have a subscription for, called FMP, which gives you a bunch of information about companies like income statement information. And so with that, let me go to that demo here. All right, so can you hear me without this for a second? Here. So I'll type in, let's say, thank you. What are the revenues of?
Font size of it?
What? Oh, font size. Sorry. Yes.
Alex is a lavalier.
Is that good? Good font size? Everybody sees in the back? All right. What are the revenues of Amazon in, say, 2022? And so what you'll see here is it prints out, oh, this was really quick, but it prints out a little bit of the tools that it's using. So it picked up this from the income statement. Then I can say something like, what were the risks mentioned in that year, for example? So a lot of times the analyst transcripts sort of like they mention risks and what they see when they recommend or don't recommend the stock, right? So so the agent again calls this ask transcripts and try to use that to give you an answer for that. So let's see what it comes back with. Doing the full retrieval with RAG here. It's just calling a simple API. It's calling the full Vectara thing, and yeah, so it gives, this is the answer it got, and then it prints out the risks. And then Suleman, for you, I'm going to say, oops, I'm going to say, what is the weather, right? And that's another thing about agents is that it knows it's a financial agent, and so thank you. So it would not answer that, right? So you can ask it, you can give it some guardrails and make it really work well. So that is the financial. That this demo actually is available on our Hugging Face account. If you go to Hugging Face /Vectara, you'll see it there. And again, stay tuned for more on Vectara agent. And so with that, let me go back to the slides here. All right. So if I wanted to pause before our next call just to see if there's any one or two quick questions from the audience for Suleman. Yes.
So just a quick question, like what if instead of like folding local functions, the functions are actually an external API, we have like thousands and thousands of functions. It's not like only 10 local functions that are actually running locally. What if this API is actually changing? I mean, usually, let's say, for an example, Facebook API, like it keeps changing, so you could have like these breaking changes. So how would that work? Do you like put a RAG layer on top of the API? Like how does it work?
If you can repeat the question also.
Yeah, sure. So the question is, what if instead of like the 2 or 3 local functions I showed you, you have like thousands of functions to choose from like an API repository or in the functions that are constantly changing? Yeah. So there's 2 answers to that. The first one is like there's one LLM that's specifically fine-tuned with that. It's called Gorilla Open Functions. And it has like a huge function API repository that you can just ask it and it will choose from that repository. Now, the issue with that is, number one, as you said, the functions might change. So and it has in its pre-training data an older version of that. So that's like an excellent case for RAG. Essentially where you have something like Vectara where a function changes or an API changes, you can update it there. You don't need to fine-tune the whole LLM again. And if you ask it a question, the LLM can actually say, ask Vectara what the API for this is. Vectara can return the function and it can call it. So yeah.
Is this the agentic Vectara is going to be released?
Yeah. So Vectara agent, as I said, is coming soon. Yeah, so you'll be able to use it soon, and we appreciate any feedback you can have on that. And one more question at the back.
So I'm assuming this function calling and the tools used are the minimum for creating an agent. Is that a fair understanding?
I would say, as Suleman has shown, function calling and tool use is a basic kind of tenant that you have to have for agents. But agents have, I think you mentioned it at the end a little bit. There's the loops and there's all kinds of algorithms of planning how to answer the question in different ways. There's a lot of work around this, and I think it's kind of an evolving field, I would say. So that's where there's a little bit more.
So now the question. So how do I know a particular LLM is agentable?
How do I know if a particular LLM is agentable, meaning doing function calling and sending JSON responses?
Yeah, so basically, I mean, the LLM kind of guide on Hugging Face will tell you if it's, so for example, that's the biggest difference between Mistral 0.2 and 0.3. And if you look at like the update logs, they will say, okay, we improved performance on function calling. So usually people who build LLMs kind of tell you what the limitations, capabilities are.
Okay. Yeah. Thank you.
All right, and thank you. I think we're just for time, we're gonna stop here. There is, as you know, a Q&A forum, so you can keep asking questions there. We'll try to, as best we can, answer them at the end. And now I'd like to introduce Nikhil, who's gonna take us through the next talk. Thank you, Nikhil.
Hi, thanks. I'm Nikhil Bysani. I'm a software engineer at Vectara, and I'm basically going to talk about like the data flows in RAG, how you can get basically state-of-the-art performance doing, retrieval generation. So we have a different mix of people here, so I'll try to go kind of give a broad overview and go into details on some interesting stuff. So just what RAG is it's basically has two main, I think, pipelines. One is structuring the data so that you can retrieve it, and two is doing the generation while retrieving it. So you have the ingestion and retrieval pipelines, and they're both basically complicated ML pipelines. If you want them to basically have a state-of-the-art performance, you can do naive things and you can do complicated things here. This is like one example of like what you could do here. What retrieval augmented generation isn't is it's not a source of truth, right? Like generally what I think when people say what we think of Vectara as a service and what we think is that your data is something separate. And we want you to be able to figure out how you structure your database into a way that we can present to an LLM, right? So in the same way that you have different indexes and different, a fan out from your enterprise source of truth, you would then fan out to Vectara and be able to iterate and change your data such that it can be presented and used in retrieval augmented generation. And so that's why, we think that, we need to store your data, but you need to be able to iterate and figure out how to store that data such that, you can use natural language for the LLM to actually retrieve it. LLMs are natural, language models. And so what they know is language. And so that means to retrieve data, they're going to use language. So that, and we have done a lot, the software industry has done a lot of research and techniques to do information retrieval on language. And specifically, we can use those techniques to structure in such a way that LLMs can then augment themselves and get the most up-to-date data. So to actually do that ingestion, I think, there's a system of ingestion that works best such that we can retrieve it for natural language. Basically, what Vectara focuses on and what usually people mean by retrieval is some kind of semantic search. You can mean retrieval could mean almost anything, right? It could mean just like a keyword search index. It could mean, just MySQL doing a like regex expression. But like the most, basically a state of art, the best retrieval you can usually get is something like semantic search, which is using transformers and encoding to change your documents into vectors and figure out what semantically most matches what the LLM is looking for. And that means that to take your data, you need to change it into a vector, right? You need to change your data into a semantic space. And you can't, and your data is probably like, you have multiple your data is basically has distinct semantic spaces, right? You have a document, it has paragraphs, they mean different things. You can't, thanks. You can't, you want the LLM to, depending on the query, most match the semantic meaning of that closest within, within your data. And so that means breaking up your data into different distinct semantic meaning, which is like very abstract. But semantic distinction is actually pretty easy with natural language, at least first pass, because we have text in sentences and paragraphs. Sentences and paragraph chapters, those are distinct semantic spaces. So we can break up as a first pass into semantic, into paragraphs or sentences, and those will basically be good enough to have distinct meaning. And then we take that we can take that into different parts and figure out from those parts what to give to LLM. You can also feed direct raw PDFs or websites, and then we can try to basically automatically break it up. Yeah. In general, we found that sentences work pretty well to break semantically. Sentences themselves are usually whole notions. And an LLM can actually take in more context. So in that sense, sometimes we've actually found breaking it up farther into paragraphs works better. Sentences might be good for basically search-based applications, but bigger application, for LLM-specific target usages, paragraphs or even bigger work pretty well. The problem is a lot of the places within a ingestion pipeline and an LLM have a max, right? You can't just dump everything into into a vector or into the LLM, into the different models. So it's really kind of a art. You need to basically be just right. Can't be too hard to code. There's a lot of like kind of data, complicated physics going into like how I transform my data, my documents into individual parts. For example, like our state of encoder is called Boomerang. It has a max of 512 tokens. The generation LLM was going to have a max of tokens, and so are the other parts of each part of the pipeline. So the end result of the search results can only be so big. The parts of your document can only be so big. And then there's a huge right amplification effect too. When you store your document, if you store it in too many parts, you're going to like 10x, 20x your size in the database. So you need to be careful on not having too much size so that the searching takes too long, and that but you still want it to be able to pull out individual parts. In general, we found out there's like a 10x rate amplification on basically ingestion, but it can be bigger or smaller, again, depending on your database. That's why our database is separate from your source of truth, because you need to iterate and figure out what the best basically footprint is. The one good thing is, despite all of this complicated, we only charge on input size. Yeah, no question.
Yeah, but the previous slide, what do you mean by 10x right amplification?
So you have your you have different sentences, they get encoded into vectors, right? A vector is there's a series of floats, probably actually bigger than a sentence. So that means if you encode every vector, your sentences are going to grow in size. And then if you're going to have multiple types of indexes, right? You're going to have a keyword index, probably like a metadata index. So you're going to basically fan out your document into like vector indexes, which and those dense indexes can actually have a lot of consume a lot of space.
Okay, all right, thanks.
Yeah.
So when you're in the vector database, the ANN basically doesn't really matter. I mean, the search is very, what do you call it? It's quite fast. So I don't understand the 10x why it should so slow down unless you're doing some other hybrid search over there.
You can repeat the question.
Yeah. Well, so he was asking why is it slow?
Yeah.
I guess I wasn't implying that. Huh?
Yeah, explain that it's the size, not the speed.
Yeah, so I was talking about the size of each component and how the encoding, right? So, Vectara takes pains to make it fast. And even though so the more data you have and the larger you amplify your data, of course it's gonna be slower, right? Search is basically,
We can discuss later, but I'll let you continue.
I mean, well, generally search speed is a size of space, right? But like, there's other things we do that's not always true, I guess, but yeah. But like mostly here, I was not talking about latency. I was talking about storage space increasing. Yeah. And the point is that I think RAG is still new. Figuring out just the right context and just the right it is still a kind of an art, right? Being able to split it into different ways for different use cases is very important. Depending on your corpus, depending on your data, is important. And you can't confuse LLM either, right? You don't want too much context, but you don't want too little. You don't want irrelevant context. So that means fast iteration using a API, a system that can keep on changing and keep up to date. And so that's kind of the theory behind separate system. Don't pollute your database. Don't change your source of truth on every time you try out something new. Use a separate system, use Vectara to figure out what works. Now, now I'm going to talk about the generation pipeline. So the generation pipeline, just to go over, is like to achieve the best generation for a query. And there's three things for that: is retrieving the most relevant results, retrieving just the right amount of relevant results, and definitely don't have irrelevant results. And you can use further techniques like we've talked about earlier in this, basically event about you can also use agentic self-querying to further refine your search such that when the user takes the query, then the LLM decide what actually goes to the database. And so that can be very powerful with the user not knowing that. You saw that with Ophir's demo. The user doesn't know what the database is, what the LLM does. And so then the LLM uses Vectara, uses the retrieval to choose the best choose the best filters, choose the best boosting, and you can give it all that information. So, a retrieval database to give the best results it's not just semantic search, right? You can do regular filtering. You can, if you know it's products, you can filter by product rank or product sizes, stuff like that. It's very important that you basically be able to figure out what best suits for the generation by using the most sophisticated retrieval possible. So you can basically have as much relevance as possible. And part of that is, one, you can expand the document. Once you find a semantic match, you can expand the context around that semantic match. And the hard part is not having irrelevant results. This is kind of an unsolved problem, especially at scale. We found that basically having a cheaper transformer model like a re-ranker, we just released a really powerful re-ranker that will eliminate and basically have the best relevant results. But that means your query pipeline becomes a series of basically transformer models or other models. And that's how you can best judge the irrelevant results. And then we're going to come up with soon, but you can also have the generation check if the generation is factually valid. So basically you can check relevance, then do it, keep on having guardrails. And none of this is perfect, but we get really good. And then I've just talked a lot about a very complicated system with multiple models, multiple storage costs, CPU and everything. Like, how much does that cost me? It's actually pretty hard to figure out. because you have a lot of heterogeneous resources. You have CPU, memory, storage, fast disk. All of these things, have overhead if they're not constantly in use, right? If you have a GPU, unless you have enough throughput, you're just paying for it. And it's not like, Lambda or something that you can have instantaneously. So what Vectara lets you do is like we amortize the cost. We basically have a simple pricing structure such that you don't have to worry about doing all this financial engineering yourself. And so that's kind of a broad overview of Vectara and the data architecture. Yeah.
So some of our clients are worried about the data privacy if they're doing RAG models and they're loading it in. So does your product store the actual documents and the vector database behind the firewall? Does it share up into the LLMs? How do you deal with privacy?
Repeat the question also.
Yeah, can you actually say that louder? I didn't quite, maybe you can repeat the question.
Yeah, I think the question was, if I heard it correctly, is that how do you deal with privacy where the data is going to the cloud and then it goes to the LLM, right?
Some of the customers like use OpenAI, they have their storage, you can go in there and then use a pseudo RAG on their product. But then that's going into their model.
Sure.
And on yours, do you have a firewall there that the actual document and the actual vectorized document after that is behind the firewall? Is that encrypted? And does that ever get passed up into the LLMs?
So the question was, do we have a firewall or any other mechanisms of security to make sure that the data doesn't go and get stored or trained on? I mean, I think that to me, I'll answer a little bit and you can add. To me, the concern is always who knows what the vendor who gives you the LLM is doing with the data. Can they train on it? Because they sort of have an incentive for that.
But if you're passing a query, vectorizing the query into an LLM, you're not passing any data in. You're just going and getting results based on.
Right. So in our system, all the data, of course, we have a lot of security mechanism in place. Everything is encrypted and transferred. That's one of the things that we do for you. And as thank you, Nikhil, for giving this talk, because I think it gave a lot of that in depth about how complicated everything is. Security is one other complicated thing that happens, and how we guard the data and make sure that it's just used for the purpose that you wanted, which is just for retrieval and to provide to them. But please.
Yeah, I think what specifically you're talking about is basically textless vector search, where you just so we have built that out. You can technically encode the data, and we would never have knowledge of the text. It's pretty hard to use LLMs with the vector store not having a text. And the problem is a lot of retrieval indexes probably want some amount of text. Maybe Amin wants to talk, but for example, keyword hybrid search, filters, all of that needs that. So Vectara takes a lot of painstaking things to encrypt the data. Like no one on the engineering team has access to your data. The keys are separate. Like I couldn't, go grab your data if I wanted to. Amin couldn't either, and Ofer couldn't either.
So the concern for a lot of people is that you have all these documents, they're proprietary to your company. And you are storing that locally, and that data is never integrated into a larger LLM. That's the main concern.
Right. So to repeat the question is like the concern is not to have the data in a separate vendor and not to send it to other people. So when you're doing, of course, we're basically going to send the minimum amount needed to our vendors. It's not like we know your data is precious. We don't want to send it to anyone. We have a SOC 2 report listing of vendors. We don't just like dump your entire database into ChatGPT or something. And then we ourselves have very strong security guarantees.
And we support VPC modes and premise, but more expensive.
Yeah, and we are coming out with, if we want to, we will deploy to your VPC or even your own private on-premise if you want.
Thank you.
All right. Well, a big round of applause for Nikhil. What? Oh, there's one more question.
One more.
Okay, one more question. Sorry.
Oh, yes. Is there time?
Yes.
Yeah, we have a little more time. Yeah.
Explain how re-ranking works a little bit.
I think maybe we can take that question at the end and keep that. And we have a question answering session at the end. So let's keep that for the. But a big round of applause for Nikhil. Again, I just wanted to emphasize how the way I view this whole topic, which is, in 2023, everybody was building, chat with one PDF with 10 lines of code or something, and it seems easy. But I think what you've seen from Nikhil and all of us, we do a lot of work to tackle it when it's at enterprise scale, and we have hundreds of thousands of documents and security concerns and privacy concerns. And we do all this work for you, and it's really quite difficult on your own to tackle all of this work, and that's really part of the magic of the Vectara platform. So, all right. So before I go to the next talk, I wanted to give you a couple of highlights of things that are new in our platform. So we recently launched Vectara API v2. We had a lot of feedback from our developer community, and Vectara API v2 is resource-oriented design. It's much cleaner, it's much nicer. We also took the opportunity to change some of the defaults, etc. So please, if you're interested, take a look at this. It's kind of the API going forward. Here's an example of how easier it is to just run a query with this new API. So that's one thing I wanted to kind of mention. And we have a big blog post about this. We'll get to the question about the re-ranker at the end, but just again to mention, we did launch a new re-ranker that is really good in terms of performance. You can see some of the graphs here. Again, there's a blog post about this on our website you can take a look at, and really state of the art. And primarily, one of the things I like to emphasize is that this ranker is really good with multiple languages, so not just English. It works really well in a lot of languages, which is really important in RAG2. Taking care of the language situation across all of your components, embedding model, re-ranker, LLM, etc. And the last thing is, and some of you may have heard this before, but we have this open source model called HHEM, or Hallucination Evaluation Model. And it's very popular because what it allows you to do is to essentially take a summary from an LLM and a RAG output and really score it, in terms of whether it hallucinates or not. Very useful thing. But one of the other thing we have is we have this leaderboard that I've shown you some of it here, that you can rank LLMs by their likelihood to hallucinate on a data set that we have. So as you can see, not all LLMs are the same. Some are better than others. And so this is, of course, an evolving thing. And but if you're interested, you can use this open source LLM. But of course, we also have this pre-computed automatically for you in multiple languages in our platform. So when you use the API with Vectara, you get that, we call it FCS, Factual Consistency Score. Sorry, I can't speak today. So that's another thing that's available. It comes out with a query automatically for you. It's pre-computed. And kind of a little bit of an upcoming thing is we're coming soon with HEM v2, which will be better in a lot of different ways. And watch out for that announcement coming soon. All right. So those are the three things I wanted to mention. And then I will now call Roger to take us through the last talk of the day.
Hi, everybody. I hope you are still staying with me. So I am the other Roger from the Vectara's machine learning team. So the topic I would like to share to you guys is about the method for reducing hallucinations in large language model. This talk is gone a little bit into the latest recent research in LLMs, and I hope I can share some of the experience of me using this method for you. First thing, hallucination, you might have heard. This is like the major defect of like LLM that making the thing even more usable. The thing is that the LLM sometimes makes things up, or what we call it, generate non-factual text. Just like the fake example, I gave it on the screen here. So when you ask the question to an LLM, what is the capital of Washington State? instead of giving you the right answer, the Olympia, it might give you like Seattle. And you might also heard that RAG is actually a solution for hallucination. What RAG, retrieval augmented generation, is basically you are just hooking up a search engine before you ask a LLM. You would first search into the thing you want to ask and then get some relevant information that feed into the LLM and hope the LLM will use the information you feed to give you the right answer. Just like this example, the context I feed it to the LLM is a passage of the Wikipedia. And you can see that in this passage, it says Olympia is the state capital. Well, then if we have RAG, does everything solved? This comes to the critical question of this talk. Will the LLM always use the search results you feed to summarize? Well, the answer is not always, obviously. Then thanks, Offer, for mentioning this Hughes hallucination evaluation model leaderboard first. So this, again, is a showing of the leaderboard. It measures the likelihood of hallucination in summarization tasks specifically. As you can see here, even the best performing model, the GPT-4 Turbo now, has a hallucination rate around 2.5. What this table tells you is that even you have RAG, you cannot always trust the results that LLM generates for you. So that brings the topic today. Here I want to share some of the method for reducing hallucinations in LLM. There are majorly 3 topics here. The first kind of method here is a decoding strategy you can use at the inference time for LLM. And the second method is a kind for fine-tuning your LLM to make it more towards factuality. And the third kind of method here is we call post-editing. This happens when what can you do when you actually have a LLM generated response? So let's first take a look at the decoding strategies. Right now, major LLMs that the popular choices are basically decoder-only transformers. So when this LLM doing generation, it have to generate token by token, one by one. And this greedy decoding strategy is one of the popular choice for LLM. You might have heard it. What it does is basically when you want to choose a token for the next token, you always choose the one token that has the highest probability. As the example, I put it here on the right-hand side. So after you're generating the token the, then for next token, you have like 3 choices here, dog, nice, and car. And here you are showing the probability of this distribution of this token. So you can see that the dog has a probability of 0.4, nice is 0.5, and then the car is 0.1. Then for decoding strategy like greedy, you will always choose the best one, which is nice. And then you do the same thing for the next token. Then the sequence becomes the nice woman. And for this, you will have a overall generation probability for the sequence the nice woman, which is 0.5 times 0.4, and then it's 0.2. However, there's another sequence that actually have higher overall probability. You might have noticed. So here, if you take a look at another pass here, the dog, first it only have like 0.4, but however, if you keep generating and then you met this has, if you choose this sequence, the dog has, then it has a probability of 0.36, which is higher than this 0.2. So this is the drawback as we talk about the greedy decoding strategy, because you're only selecting the token that might seemingly has the highest probability does not mean that the overall sequence has the highest probability. And how does this have to do with hallucination? Well, the thing is that since you are only looking at the greedy path and a factual or more high quality, the response may be in some other decoding passes. Just like the example we showed you, the dog actually has greater probability than the nice woman. So to solve this, you also might heard another decoding strategy, which is called beam search. The biggest difference between beam search and greedy decoding is that instead of keep tracking just only one pass that used only one token, you are actually tracking more than one pass. For example, this is an example when we use the number of beams that equals to 2, which means you are always tracking the best 2 sequences, starting with generating the token. And then we are looking at for the choice for the next tokens. The dog and nice has the top 2, are the top 2 choices. And then within that, after that, we also keep tracking the next 2 best token for each of these 2 sequences. But then finally, you only keep track 2 paths during the generation. So you would discard the other 2 choices, and then instead making the path into 2 paths. And finally, by doing beam search, you got the more overall higher probability sequence, which is the dog has. And how does beam search actually perform? So let's take a look at the HHEM leaderboard results. We take an open source model to experiment with different decoding strategies. The model we used is Mistral 7B. Compared with the greedy decoding, when we use beam search with number of beams set to 10, you can see that the hallucination rate actually drops from 6.8 to 4.7. That's almost like a 2% improvement. Well, the advantage of using beam search is that it is very easy to implement. Suppose you are using like major inference frameworks like Hugging Face or VLLM, or even OpenAI. They have this option called number of beams. All you have to do is to set the number of beams to the number of sequences you want to track, and that's it. And this kind of method, it does not need you to change the model at all, just change the generation parameters. But there are some like trade-offs when you are using beam search. The first thing is, since you are tracking more than one possible sequence, it will take extra inference time when you're actually generating the answers. And the second drawback here is that it is not stream friendly. By streaming, we mean that you want to see the token generation in live, which means you want to see the token generated one by one. But however, for using beam search, you won't know which sequence is the best until you reach the final results and do the sorting. So this basically not able to do streaming if you use beam search. Okay, so beam search is one of the decoding strategy you can use, and this is not new. This beam search is invented like a long time ago. So let's look at more recent technologies on how to make the model more factual when at the decoding time. So this paper called DOLA, Decoding by Contrasting Layers Improves Factuality in Large Language Models. This paper is a recent paper by MIT and Microsoft. It is published on iClear 2024. To summarize what the paper do, basically the model is changing the output token distribution during the generation. And how did the paper manage this? Let's take a closer look at it. Well, the authors of this paper, they claimed the 2 kind of intuition between the for the DOLA paper. The 2 intuition here is that they find that early layers in LLM encode shallow information, while into the later layers in LLM actually encode more semantic or knowledge information. Well, this makes very sense because as the layer goes deeper, the thing you encoded in LLM the representation become rich, more and more richer. And they also made two kinds of observation during the decoding. They find that important entity tokens are determined in the later layers in a LLM, while the easy tokens, something like the, or, and, some function words or connection words are actually determined earlier in the middle layers. What this observation tells us is that they find the later layers output actually is more important than early layers. And how do we utilize this observation? That's the thing we're concerned, right? What they proposed is to emphasize the final layer output while downplaying early layers. Let's take a look at a concrete example on the right figure. So for the question you are sending to the Llama 7B model, the question here is, where is the capital of Washington State? That's the same question I just gave you guys in the earlier slide. You can see that the correct answer, Olympia, actually starting with a very low probability in the early layers. But as the layers goes deeper to the final 32nd layer, you can see that the Olympia's outputting probability actually got higher. However, this not correct answer, Seattle, also have like very high probability in the end, making it almost equally that have a 50-50 chance the model could output Seattle or Olympia. But the author discovered that if you contrasting the output token probability between the 32nd layer and the 16th layer, and making it the token distribution like on the right-hand side, you can see that the wrong answer, Seattle's probability actually goes down. The correct answer, Olympia, become the only top choice for the next token. So that's the intuition behind and the principle behind this paper. How they specifically implement this method, they have made a two-step method. The first step is you have to select a layer to contrast. And the second step is to altering the final prediction. For selecting the layer to contrast, all you need to do, according to the author of this paper, you need to select the layer that has the most different output than the last year. You have to choose a layer from the middle layer from that. And what you can do is you can measure the difference using this Jensen-Shannon divergence. This divergence is a metric distance to measure the difference between two discrete distribution. And using the JSD or Jensen-Shannon divergence, after you selecting the layer to contrast, the second thing you need to do is by contrasting them. Well, this is also very easy. All you need to do is just to do subtraction. You just subtract the layer output probability from the last layer of the last layer, and subtract it to the selected layer output. Okay, and then looking at the figure on the right-hand side, you can see that the question is, where was the author of the theory of relativity from? So the answer is Albert Einstein was from German. As you can see, during the generation process, using the algorithm they proposed, they will select different layers to contrast and outputting the final factual consistent answer here. Well, that's basically their method. But all we're concerned is about how this method perform on like the RAG scenario. Well, taking a look, we take this method and plug it into our experiment. So here we are also using the same model we just used for the beam search and also the greedy decoding. You can see after plugging the greedy decoding method also and with the DOLA decoding method they proposed, the hallucination rate has a little bit drop, about 0.5%. yeah, you might find this result not that promising. Yeah, we have to admit that. So this paper, there are several explanations. So first, this paper, when they proposed, is not for RAG scenario. This paper is more like eliciting the LLM's factual knowledge from its parametric knowledge. But again, this method also has its advantages. First, it's streaming friendly if you are stacking DOLA with greedy decoding. And then also because what this paper essentially do is just changing the output probability. It does not have to do with other decoding strategy. You can also use beam search on top of DOLA. But then there are also some drawbacks of this method when you actually need to consider when you deploying this method. First, it needs some code changes when you do the inference. When considering like major inference frameworks like Hugging Face or VLLM, it doesn't support the DOLA method by default. Because like for this method, you need to get the output token distribution from different layers of LLM. Usually, what we got from the inference framework is just the output distribution from the final layer. Also, it needs to choose which layers you want to contrast from. So that's another hyperparameter you want to tune. Okay, that's basically for the first kind of method I want to share. What we just talked about now is how you can use beam search or DOLA decoding methods during the inference time. The next part of the speech is how you can actually fine-tune your model, making it towards factuality. On the right-hand side is the figure of training a LLM that is proposed in 3 stages diagram. This diagram is first mentioned by OpenAI's paper called InstructGPT. To make a LLM, you need to perform a 3 stages training. First is pre-training, then do supervised fine-tuning, and the third step to reinforced learning with human feedback. And what essentially the third stage do is you want the model to align with human values. Something like you want the response to be safe, to be honest, and to be useful. So since they already done some research on aligning on safety, honesty, and usefulness, can we also use the third stage method for aligning for factuality? Well, the answer is yes. Before we go deep into how we can actually fine-tune a LLM for factuality, I want to introduce this algorithm called direct preference optimization. So this is also an algorithm for fine-tuning LLM on aligning for human values. All it needs is 2 things. The first thing is preference data. The second thing is BCE-like loss. The BCE-like loss is what we call binary cross entropy loss. So first part, the preference data. For the preference data, you need 3 things. First is a prompt. That's basically any data you would have. And you also need multiple responses from a LLM. And then within these responses, you will need to annotate like which responses you prefer and which responses you do not want them. So this data becomes like chosen response and rejected response. That's how you construct the preference data. Usually what we do is we ask human annotators to annotate these data for you. And once you have this preference data, the next thing you need to do is to fine-tune the LLM on this data. Using the DPO algorithm, what it essentially do is it will increase the likelihood for your chosen responses and decrease the likelihood of the rejected responses. Specifically for fine-tuning factuality, there is a paper called Fine-Tuning Language Models for Factuality. This paper is by Stanford it is presented on iClear 2024 poster. They did exactly the thing we wanted. So they used the DPO to fine-tune for factuality. In their paper, they provide a way to construct the preference data automatically, but their task is for like biography generation and medical QA. So here we are providing a reproduction of this paper, but our setting is a little bit different because we are concerned about the RAG scenario. So we did this alignment experiment on the facts for fine-tuning the model on summarization factual consistency. So then the first step here is that we need to construct the preference data. What we do is we sample the response from the open source Mistral 7B model. We use the temperature-based sampling method to get a multiple different response from the same model. We set n here, number of responses is equal to 6. And then the source data we used to generate the summary is from this 3 dataset. The CNN Daily Mail dataset, the BBC XSum dataset, and this vitamin C dataset. So then the next step, you will need to ask a human to annotate like which summary is more consistent than others. But you know that it's very costly if you want to hire people to do annotations for you. Luckily, we don't need to do that with the Vectara's HHEM model here. Well, with this model, we can rank the model responses by its factuality automatically. What we did here is we choose the factual samples as the HHEM model's score better than 0.8, and the rejected responses are the summaries that has HHEM score less than 0.5. And finally, after we constructing the preference data, we can do fine-tuning using the Hugging Face, the TRL library, and using LoRa on top of it. And this is the result we have. You can see that after you actually do the alignment using DPO algorithm and the data we created, the hallucination rate compared with like the initial greedy decoding and using the original model, the hallucination rate actually drops 2.6 points. This is very effective. Well, so talking about the advantage of this method, first, instead of changing the decoding strategy, you are changing the models. So this means like you can also stack other decoding strategies on top of the model you just using DPO to fine-tuned. However, to use this method, first thing, you need to construct the preference data. And then the second thing is you need computational resource to actually fine-tune the model. So that's basically the second kind of method for aligning your model for factuality during the fine-tuning times. Lastly, I want to share the third kind of method for mitigating hallucination in large language model. It is called post-editing. For this kind of method, you actually do it after a response is generated. As you can see on the example on the right-hand side, first, your large language model may generate a factual inconsistent sample here. It said, scientists believe a vaccine for Ebola might not be ready this year. The first vaccine for Ebola took 5 years to be produced by the CBP. Well, this model is hallucinated, and the text in red actually tell you where it is wrong. So first, it mistakenly put COVID-19 as Ebola. And then the approved is becomes produced, and finally the FDA becomes CBP. What post-editing do is you use a model to actually correct this inconsistent summary and to make it a correct or consistent summary. The paper actually do this is this paper called fine-grained hallucination detection and editing for language models. This paper is published by the University of Washington, CMU, and Allen AI. The model they produced is called FAVA. Basically, the model just taking the source input and the generated incorrect summary into the model, and the model will change the output summary to give you a consistent summary. The most important thing about this paper is they constructed a way to actually generating the inconsistent summary and the consistent summary pairs and train a model upon it. What they do is that they generate the synthetic inconsistent response by prompting GPT-4 model. Taking a look at the concrete example from the figure, it asks the GPT-4 to actually change a factual response into a hallucinated one. It prompts the GPT-4 model to insert a relational error into the passage. What it does is, like, you can see that the original text is Lionel Messi relocated to Spain at 13. Then the GPT-4 model change it, becomes Lionel Messi relocated from Spain at 13. By doing this, you can generate the post-editing dataset automatically. And then the next thing you need to do is to train a model to actually perform the editing for you. This is an example from the demo of the FAVA model they prepared on the Hugging Face page. Unfortunately, their demo is a bit down, so I cannot perform the demo lively for you, so I copied the text from their web page. You can see that the text in blue here is the references to generate the summary, and the purple part is the hallucinated summary. And the last thing, the dark red text are the edited text by the FAVA model. First, it detects like this 1886 is a hallucination because in the reference it says that the Banff National Park is established in 1885, so it corrects this 1886 to 1885. And then it also discovered one invented sentences and subjective sentences. The invented sentences says it recently won a Nature's Choice 2023 award for its beautiful mountainous terrain. Well, this text is not presented in the reference. And also, it's the best national park ever. It's also never mentioned in the reference. Let's see how this model actually perform our HHEM leaderboard. You can see that after applying the FAVA model to correct the greedy decoding response from the Mistral model, the hallucination rate drops a little bit, 0.5. You may say that this correction rate is not that much. One probable reason is that the data they trained this editing model is using GPT-4 to prompt it. And this prompt method is like too weak. The synthetic method is too weak to actually mimic a true hallucination response. So they failed it. But still, the model can act as a basic check for your generated response. The advantage for this method is that it is an individual component. You don't need to change anything on your decoding strategy or change any already deployed model. All you need to do is hook up the FAVA model after your model has generated a response. As for the drawbacks, because you are using another model for correcting your summary, you might need extra, you may introduce extra latencies to it. And as we said, the correction quality majorly depend on the data you have. So it is also data dependent. Finally, I want to do a summary of the method I just introduced you guys. So firstly, I taught you guys two methods in the decoding strategy at the inference time, they are beam search and DOLA. And for the third method here, DPO on factuality is the algorithm you can use to fine-tune an LLM for factuality. And finally, post-editing is what you can do after a model has already generated its response. This table summarizes the advantage and disadvantages of using these different techniques. And finally, we have like the demo and all the code and the notebook at the GitHub repo here. You can reproduce our experiment using the code in the repo here. One thing I want to mention here is that some of the methods can actually be stacking together. Like for the last result here, I used the DPO to fine-tune a model, and then I used beam search with the number of beams is set equal to 10. Actually, you can find that this Mistral 7B model, after doing these two steps, its hallucination rate drops to 3.1. This is actually a very promising result because it's reaching the GPT-4 level result. At the end of the slide, I want to say something about like some other techniques that is not covered by this talk. First is like you would want to improve your retrieval result for doing RAG to avoid at least reducing the number of irrelevant context for LLM to generate the response. The second thing is query rewriting, as the one mentioned by the Nikhil and the author before. You can try to do query rewrite to ask the LLM to better to reform the query so the LLM can better understand what you need. And third thing is you can try like prompt engineering using chain of thoughts to improve your response qualities. And I think that concludes my share today, and I'll return the mic to author.
Thank you very much. Wow. Stay here for a second. Yeah, thank you for that talk. Wow, very deep technical talk, research. I'm so glad to see that there's a lot of work being done on reducing hallucinations with so many techniques. I know none of them are perfect, but I'd like to get the one that reduces the most, streams, has all these advantages. So we'll get there in a little bit. A couple of questions for Roger. Yes.
Yes, on the beam search, you consistently use 10, that you do trial and error. You mentioned 5 or anything like that, and you talk about the pros and cons. I assume it's going to require more time and more resources if you increase the number.
The question first.
Yes. So the question is, have I tried like using different number of beams and see like what's the latency changes or the hallucination rate changes? The answer is for you is no, unfortunately, because due to the time constraint, I haven't be able to done all this experiment. But that's a very good point. I can add this back to the benchmark someday in the future.
Over there, yeah, please.
The model that had the 3.1 error rate, did you test it out with Fava at the end to see if it affected any further?
Yes, we can definitely add Fava to it. Also, due to the time constraint, I haven't been able to conduct that experiment. But I'd expect the hallucination rate can be also dropped in a little bit further. But the effect won't be that strong because like the Fava, the data that used to train the Fava is actually very weak.
Yeah, so excellent talk. I mean, like you covered all the bases, so very good talk. When you go back a few slides, you kept the temperature at 1, right?
Yes, for the DPO.
Right, over here at 1, and then you basically had the responses being looked for factualness and all. What was your reasoning for 1? Why didn't you go further down, like 0.2 or 0.3, where you would have had consistent? Why couldn't you start with a better data set? I want to understand your reasoning why you use 1.
Okay, so the temperature, the question was why did I use other temperature settings for generated the DPO dataset? So first, temperature is a parameter to control the deterministic of the model response. With lower temperature, your model response will become more consistent. With higher temperature, your model response will vary much, like generating like even different styles. The reason I set temperature at 1.0 is because I wanted more diverse response to be able to generate the preference data set. So I need a rank of the summaries, like which being from the most consistent one to the least consistent one. So that's why I use the temperature of 1.0 to generate actually different summaries.
All right, so thank you again for that. I think we have about 10 minutes for any questions that we didn't get to do during the actual talk. So now, Nikhil and Suleman, if you don't mind coming here so we can kind of tackle any question. And also, Tony, if we have any questions from sort of the online folks, we can definitely tackle those. But let's get started. Why don't you go first?
Re-ranking question here.
Yes. Actually, it's a good point. Let's start with the re-ranking question because I promise we'll do that. So why don't you start and then we'll go after that. What was the question again? Can you please repeat it?
It would explain how re-ranking works.
Can you explain how re-ranking works?
I think we should give it to the person who actually built our re-ranker. So
okay, so basically like so I'm Vivek. I'm a machine learning engineer here at Vectara. And so like basically your question was like, how does re-ranking work? So re-ranking basically is a broader term that can encompass changing the search results in the way you want. In the context we use re-ranking over here was boosting relevance. So let's say when you search and you take the top 20 or 30 results. And so your search results are ordered in a fashion, but the relevance order might not be that good initially. So the purpose of the re-ranker model is to make it get the re-rank or the ranked results to as close to the ideal order as possible. So basically the most relevant result should be closer to 1. The next relevant result should be closer to 2. And how it's achieved is, so basically using a neural search model or an embedding model, we take a query and find, let's say, 30 or 50 most relevant passages. And then for each of these query passage pairs, so for one query, if you retrieve 50 passages, so basically you have 50 query passage pairs, and you pass each of these query passage pairs through the re-ranker model one by one and produce a score. And then you order those passages based on the score produced by the re-ranker. So basically that's how.
Thank you, Vivek. If I should stay here, and if I can add one more thing is like, I think what Vivek is mentioning is usually called a two-stage retrieval model, right? Where you do first something you can't run a ranker on 1 million documents, right? That's just not scalable. It will take too much time. That's why, like Vivek said, you first get, say, 50 results or 100 results that you can do with an embedding model or a hybrid search or all combinations of these. And then it's feasible to run a ranker in real time on those results. But thank you. There was a question here.
Yeah, I'd just like to hear in general what you see your product offerings evolving to in the next 6 to 12 months, specifically around RAG.
Mm-hmm.
So the event, do you see it on the kind of induction side? Like we covered how you get your content into the vector database and how you can index and things like that. Or is it similar to what we just talked about retrieving the most relevant pieces of information and then putting that into the LLM? So I guess there's a little bit of a loaded question there, assuming you are betting heavy on RAG for the future, but just kind of like that holistic space, understanding what your thinking is.
So just repeat the question. The question was for everybody online. What does our roadmap essentially look like in terms of both ingest side and query retrieval side, assuming we're continuing to go into the RAG? Yeah, so RAG is a very, very powerful paradigm and architecture and methodology, I guess, to build all kinds of chats, assistants, and other things. And we feel very strongly that that's going to be very useful for everybody building enterprise applications. And I think our roadmap is split into a couple of different things in all of these areas that we mentioned. So continue to build and making it easy for users to ingest data of different kinds in better ways, but also at the same time, improving all the components that include sort of RAG as a service, the embedding models, the re-ranking models we talked about, call the LLMs, the infrastructure, making things more secure. Everything that we talked about today all fits into our roadmap. I don't think I can tell you how much we're going to spend on each one of them, but that's generally kind of what I would say. Yes.
So I want to ask something about the coding and the factuality that you've shown, and specifically about the dollar algorithm that was developed from MIT. I think you mentioned that because it works with contrasting layers, you should always select the final layer when constructing.
The question, please.
So the question is why it always select the last layer for contrasting?
Yeah. I mean, is that what you did? Because I think what I'm getting at is, do you think the dollar method could get like a better result if you focused on selecting more contrasting layers between them, not just the final at the end?
Yes. So the paper's intuition is that the last layer's output is actually the most important, but because the logics of last layer may be noised by like previous layers, you need to subtract one of the previous layers to get the final distribution. So last layer will always be in the chosen list, and the thing you want to choose is like one layer from previous layer to do the contrasting.
Okay, so so you don't think it can get better results, essentially?
Personally, I don't think so, because the model is always the way the model is trained is using the last layer to produce the prediction, and it's more natural to always keeping the last layer in your loop.
All right, maybe one more question. Yes.
Yeah. So I had a question regarding the Fava model and why we're not, or more along the lines of if you've looked into like DSPi's like assertion, comparing the two and that sort of area. I'm not sure if you're familiar with it or not.
The stuff for generating more data for it?
So for like the Fava model specifically, it's basically trying to compare if it's matching the retrieved text, right? That you're using in your comparison for RAG. And so I'm wondering if you guys have tried something like an assertion, like the assertion things in DSPi or something similar to that, where essentially it'll do a similar sort of comparison, doing that sort of using an assertion model or using an assertion statement where it'll assert if it actually has matched it, and if so, then only then will it continue. Otherwise, it'll have to rerun the model to get saying that this was your previous output, it didn't match here, and then rerun it with that. I'm just wondering if you guys have looked into that sort of area for hallucinations, or if that's made any sort of difference, or if it's similar to Fava, or if you haven't looked at that.
Okay, let me try to understand the question. So have I tried using the assertion operation of that is offered by the DSPi framework to actually test for fact editing stuffs? Yeah, right. That is actually very interesting future research direction. But I think the Fava paper itself didn't mention anything like that. But I guess for such kind of thing to work, probably you need to decompose like the generated summary into like atomic facts, and then do insertion one by one, right?
Right.
Then I think that's gonna be like time consuming. Yeah, because the editing model, what he wants to do is to be able to correct your summary in one inference time. But I definitely think that the DSPi method is worth exploring. Yeah, thanks.
Cool.
All right, I think we're a little bit at time. So what I want to suggest is we're going to stay here for the next maybe 30 minutes. So if anybody has other questions live, they can please grab one of these wonderful speakers today and ask some questions, or others. I also wanted to thank again Rogger for hosting us today. A big round of applause to you, Rogger. Thank you so much. And to your first question today, like who here is, is a startup, and they can reach out to you, but also reach out to us because we have a good startup program that you can join that gives you a good way to start working with Vectara. But also, if you work in a bigger organization, reach out to us. We're here to help you with anything that you want to do with the RAG or agentic RAG or anything else. And if you also have any questions, follow-up that we didn't get answered today, we have a Discord server. You can join that as well and ask a question, and we'll try our best to answer those as well.